Super, thank you very much. I have to stand where I can see the slides a bit. So first of all, thank you very much. It's a real pleasure to be here in such a lovely place and to have this chance to talk about some of the things I find interesting, and I hope I can communicate a bit of that to you. Quantum technologies, classical navigators. I was asked at one point by our press office whether I could explain quantum mechanics for a newspaper in 2 sentences. The answer was no. Today we've got 90 minutes. I'm wondering whether we can make some headway into that. Usually quantum mechanics is explained in a fairly mathematical way. I didn't think that would go down too well here. So I thought what I would try to do is to use lots of pictures and analogies. Whenever you're explaining quantum mechanics, an analogy is not perfect, but we'll see how we get on with that. So I'd like to pick on some of the quantum technologies that are emerging, and in particular those that are relevant to sensing and in the context of navigation. I should perhaps start off by asking a quick question. How many of you here are working on anything quantum? 1 or 2 hands going up? Yeah, a little bit, excellent. How many people here, I'm sure everybody's working on something inertial. How many people here are interested in the navigational applications of that? Few more, excellent, good. So let's see how we get on. Let me start off by saying this is the UNESCO International Year of Quantum Science and Technology. And the reason for that is that it's pretty much 100 years since quantum mechanics, quantum science, emerged from what had been an unsettling series of experimental results, which required a different explanation. And you couldn't really pin down an exact year, but there were probably about 3 years in which really the ideas came bubbling out. And by about 1926, then the principles were pretty solid. And you've got some great meetings like this one here, where almost all of the people in that photograph are really key names in the history of science. So it's an exciting time that 100 years on, when we're looking backwards at that, we're also looking forwards at a new range of technologies that have been developed and have been coming out, I suppose, in the last 10, 15 years, something like that. Now, the current state of quantum mechanics, I think, is an interesting one. The theory, as far as we have it, works extremely well. You can do calculations, and you can make measurements, and you can find agreement at the level of parts in 10 to the 10. And though that 10 to the 10 is actually limited both by how well you can make the measurements and by how well you can do computations, which tend to be quite difficult at that level. So if we look, for example, at one of the, I'm not going to go into what this is, but one of the key numbers in quantum mechanics here, this is the theoretical measurement with an uncertainty of 70 parts in the last places, and this is the experimental equivalent of that. There's agreement of an awful lot of digits there. It's pretty much the best tested theory we have in science. On the other hand, the interpretations are still debated, which is great if you're a fan of Star Trek. Plenty of scope there for looking at that sort of thing. And I think it's fair to say that we don't yet have a complete model that explains what actually happens, the process by which we make a measurement in quantum mechanics. We know how the before probabilistically maps onto the after, but we can't describe that properly. So on the one hand, what we've got seems to be really good, but it's not quite complete, and that makes it absolutely intriguing. So what I'd like to do today, and I'm going to limit myself slightly to what I've got up here, I'd like to introduce you to some quantum technologies, but I'll focus on the left hand of these. We might just get onto the right-hand ones, but actually they've got less to do with inertial sensing and less to do with navigation. So we'll focus on the left-hand ones. And what I'll do in explaining to you or illustrating how these work is introduce you to some of the concepts of quantum mechanics as well along the way, and how that is used and how it differs from what we might expect in a classical world. So I'll focus upon those aspects which are relevant to sensing and navigation. And I'm going to try to use some concepts from classical navigation as the examples for that. So in the tutorial, I'm going to break it down into 4 sections, really. The first one, I'd like to introduce the idea and actually make a distinction between something you might have come across, which is what people colloquially refer to as quantum 1.0, quantum 2.0. I'll explain that in a moment. We'll have a look at timekeeping as the first thing. Timekeeping, of course, absolutely crucial for navigation if you're using GPS and a lot of other things, but it's also the basis for some of the other explanations that we'll have. Then I'll have quite a large amount on the inertial measurement. That seemed appropriate for this conference. And then at the end, I'd like to look at one of the, you might be, as you're going through this, you might be thinking of some problems that we have, and you'll be absolutely right, but I'll show you an interesting way in which some of those problems can be tackled. So 4 parts, starting off with a bit of a setting of the scene. Now, I should say, please put your hands up at various times. I will stop in between those different sections and ask for a specific time to ask for questions, but I'm very happy to try to answer questions as we go along, with the emphasis on try. Along the way, and I've put this slide up mainly so you know it's there in the slide pack. I'm not going to read it out or get you to check through it now. But these are some of the principles of quantum mechanics that we will illustrate along the way through this talk. Traditionally, these are essentially a slightly expanded version of what we know as the postulates of quantum mechanics. I'm trying to remove the mathematics from it as well. Okay, so first part, let's set the scene for quantum 1 and quantum 2. What people think of as quantum 1 is the technology that we've had that's now established and it's been going on for some decades. And that really refers to the fact that it goes back to the wave-particle duality aspect, which we'll talk about in a moment. But the key feature here is that electrons, which we might think of as particles, actually behave as waves. And that is manifest in solids, cryogenic materials, atoms, and in some cases in vacuum systems as well, and leads to devices that we're familiar with. These are a wide range of semiconductor devices, photonics, solar cells, and a few that we've come across that maybe ought to sneak actually into the quantum 2.0 category, and I'll explain that in a moment. So squid magnetometers and atomic clocks, as well as the magnetic resonance imaging that you use in hospitals, I think we could say are early versions of what we now think of as the new generation, the quantum 2.0. So these are the established quantum technologies. I'm not going to talk too much about those, but we've seen the value of them. And to set the scene on where we are with quantum 2.0, I'd like to go back to the early days of quantum 1.0 and the invention of the transistor. So this is the first point contact transistor that was developed in 1947. Once that had been developed and it was starting to go, something like that was going into production with the different version, the junction transistor a year later. What you saw was a trade stand here set up by Bell Labs on the transistor. If you can't read it at the back, on the left is a panel with some telephone uses, and on the right, other possible uses. That was the state of the technology of semiconductor devices in 1950. First transistor radio was down here. That was the first product, and it was made by, I think, Texas Instruments as a use of the first commercial transistors. So how did that field develop from what looked like a fairly primitive sort of device and a rather limited range of potential applications? How much confidence was there in that? Well, 1974, head of Digital Equipment Corporation said, there's no reason for any individual to have a computer in the home. How many do we have in our homes now if you count all the microprocessors that are in your domestic electronics? And where we've got to now, can you imagine seeing that as the first transistor and being told that you can now get a chip with 208 billion transistors in it, and that the market would be a good fraction of $1 trillion. So where are we with quantum technologies? We're here. We're starting to think about these. How's it going to go? I don't know. I'm probably the worst person to ask about where technology is going to go. When the first cell phones came out with cameras in them, I thought, who would want a camera with a cell phone? Yes, well, so I'm very bad at that, but I'm fascinated by this area, and it really does feel as though it's a new, broad technology, perhaps resembling the way that transistors were in the 1940s and 50s. And what these quantum 2.0 technologies are characterized by, and of course one has to be a little bit approximate and sweeping in all of these statements, is that as well as the fact that you've got a confined wave, we'll get on to how that affects things a little bit later on, what we're starting to do is to put things together on a bigger scale. So at the device level, we're seeing effects of quantum mechanics, and these effects I'll bandy the words around: superposition, interference, quantization, entanglement we'll get onto another time, and quantum statistics. Things that are not really relevant in semiconductors and superconductors, but which are very much the basis of the technologies that are being developed now. And what are those technologies? Well, we can think about the technologies, the platforms they're based on, some of the applications up here, and different levels at which these are coming in, from principles to component devices through to overall systems. Sensing is clearly the most relevant one to an inertial conference. Timing and measurement go hand in hand with that. Computing may be relevant, but there are these other aspects of cryptography, imaging, communication. So it's quite broad in the potential applications of this. It's also surprisingly broad in the platforms. So when you started off with transistors, you were already limiting yourself to semiconductors. And although those early transistors went from point contact to bipolar junction through to field effect, so you're looking at different versions of them, we're looking at a much broader range of systems. So there are some platforms that are based upon semiconductors. There are others that are based upon superconductors. There are some that are based upon essentially MEMS devices. And then there's a whole range of things to do with individual atoms, molecules, a whole heap of applications where it works with photons. Almost every system you can think of that's small has potential for this. And people are developing applications or exploring applications using all of those different systems. So we haven't even yet decided for any of these which is the right platform to be looking at. Again, the fact there are so many makes it feel exciting, but it also makes it very difficult to predict. Okay, so that's my setting the scene. First of all, any questions on what I've said there? Any comments on this? Things I've got wrong. I'm always pleased to hear. Well, I'm never pleased to hear where I went wrong, but I'm very pleased to hear of alternative views or comments on it. Okay, let's move on. Timekeeping. Timekeeping is really one of the first examples of quantum technology and the atomic clocks that go back a long way. But it's also something where I can introduce my first analogy with classical navigation. And the one I'm going to introduce, perhaps strangely here, is the compass. If we have a compass, then the fact that the Earth has a magnetic moment, it generates a magnetic field around the outside. If we take along another permanent magnet and put it there, it will align with that magnetic field. And that system I'm going to shrink down in a moment so that we replace this with an atom. Now, if you were to do this normally, you'd just see a stationary needle, unless you're doing something a bit more dynamic. And if you're in a sailing boat, if you're in an aeroplane, if you're jogging along, I suppose, what you'll actually see is that it's really rather annoying. It takes a while for this needle to settle in the right orientation. And what it will do is to oscillate a bit around the orientation you want it to be in. Now, that oscillation will happen at a particular frequency for that system that you're dealing with. And then if we shrink this down to an atom, that same phenomenon will remain. I'll come back to that. When we look at clocks, we're generally looking for some sort of oscillation. And we might be dealing with a grandfather clock like this one. It's actually one that was built by a chap called John Harrison, who we'll come on to in a moment. And the mechanism in there is wood. But that's based upon a swinging pendulum. And that mechanical oscillation is what gives you the time base for your timing calculation. You can make that smaller. Your nice 1950s watch probably has a spring and a balance wheel in there. And more recently, you have the vibrations of a quartz crystal. Now, these are great and very well-established technologies, but they have problems. You have to calibrate all of these because no two are exactly the same. You have to work with problems of stability, that the thing will vary with temperature, in some cases humidity. And perhaps the most crucial one is that they are coupled to the environment. So if you let the pendulum swing for a while, it will eventually stop. And you have to keep putting energy into it. And that means the reason it's losing that energy is because there's some friction between it and the environment around it. So when we get on to the atomic clocks that we're looking at, well, the mechanical oscillator is now much smaller. They're electrons around the nucleus of an atom, or the orientation of that magnetic dipole, which we'll come on to. But the advantages now, when you take an atom, you take atoms of the same element and isotope, they're all identical. You've got over the calibration problem. And if we're dealing with atoms floating around in what is otherwise a vacuum, then they are not really coupled to the environment. There's no friction between them and what's going on. So they will last a lot longer with that undamped oscillation. On the other hand, the cost and size are problematic. And if you've got a free atom on Earth and you let go of it, it will drop like anything else will. And you have to get over that problem. So timekeeping, I'm going to look in a bit of detail at the first atomic clock and how that worked. And that will actually take us on in that the mechanisms within it into how some of the other quantum technologies are based. So let's introduce the first atomic clock, first of all. There's a picture of it up on the top left here in the National Physical Lab in 1955. A large piece of apparatus, but it allowed the precision of timekeeping to be improved substantially. And in fact, that precision from that point up there where it was the numbers, we can always debate over what's the relevant number for this, but this was the stability was the order of parts in 10 to the 10. So if you went counted for 10 to the 10 seconds, you might have lost or gained a second. Over time, as we go from 1955 through to, the graph runs out a little bit before today, but it's probably not too far out. We've had a gradual improvement in those traditional atomic clocks coming down to about parts in 10 to the 15 or 16. On the other hand, the new atomic clocks based upon free atoms, which have been introduced, they started off at the same sort of level as the original National Physical Lab clock, but they've improved at a steeper rate. And we've now got precisions down here of the order of parts in 10 to the 18. It's been demonstrated in the labs. Well, the age of the universe is less than 10 to the 18 seconds. So you're talking about a precision now of these clocks, or an accuracy, I should perhaps say, an accuracy of these clocks of the order of a second in the lifetime of the universe. They're based upon, in fact, they have, second is now defined in terms of the a frequency in the cesium atom, a microwave frequency down here. And we'll see why that's relevant when we go back to that picture of magnets, of the magnetic field and the compass around it. So what we find is that if we look inside an atom, roughly speaking, we have a nucleus, we have electrons around the outside, and the nucleus and the electron can both act as little magnets. And therefore, in the same way that our compass would align relative to the magnetic field around the Earth, then we'll find that the magnetic moment of the electron will align relative to the magnetic moment of the nucleus. And that again, if they're given a bit of a kick, then we'll get a wobble around there in exactly the same way that your compass needle takes a while to settle. And that has a particular frequency. And that frequency is this 9 gigahertz frequency that I've put up over here. Now, what we can do essentially is to use this as a way of, we then count that frequency, we measure how many periods we get. Every time we get to 9,192,000,000 and so on, we say another second has occurred, and that's how the timekeeping works. And that's, as I mentioned, that's a microwave frequency, so we're dealing with microwaves there. Before I move on from this slide, look how the technologies have changed from that original clock, if you like, the equivalent of the point contact transistor. First of all, they can be a lot smaller. This is, what's that, 6 years ago, National Institute of Standards and Technology in the States produced a chip scale clock using fabrication techniques from the semiconductor industry, and that's a coffee bean at the side of it for scale. That's not the most precise, that's working to parts in 10 to the 13, but still pretty good. On the other hand, the latest clock to be in everyday service, cesium fountain clock at the National Physical Laboratory, that's operating at parts in 10 to the 16. It's considerably bigger, but it looks neat on the outside at any rate. Now, I said I'd introduce some principles of quantum mechanics. If we look at the alignment of the spins in this case, there are two configurations in the atom. We can have the situation down here, which is the one of lowest energy because this compass, if you like, is now settled out. But we could potentially have that needle pointing in the other direction. And in that case, because we forced them together against their will, they have a higher potential energy for that. And what we actually find in quantum mechanics is that the energy difference there is related to that oscillation frequency that I referred to. It's given by the frequency that we have multiplied by Planck's constant. So we're starting to introduce this idea that there is a frequency related to an energy. Classical mechanics, particles will have an energy. Quantum mechanics, we'll see, deals in frequencies. Okay. So what was the insides of this atomic clock that they developed at the National Physical Laboratory? It's the basis of what we have in atomic clocks through to today. And I'd like to draw your attention to some of the features in there, though some of the details may be different. So what we had in this case was a beam of cesium atoms that left an oven on the left-hand side up here. So you have literally a sort of a bean can with some cesium metal in there. You heat it up, there's a little hole, and cesium atoms come out of that. And they head along the apparatus. At this end here, ultimately we'll detect them. But on the way, several things happen, and that's explained in this diagram down here. The first thing is, of those two different orientations, we want to filter out the atoms that are in this state. And in fact, we can do that by the fact that they will respond differently to a magnetic field. So we have a selector here, and we make sure that we're starting off with atoms that are all doing the same thing. At the end, we will do some filtering to get rid of the atoms that are still in that configuration. And in the meantime, what we want is something which is going to change that configuration. And that is two bursts of a microwave field at that magic frequency of 9.1 something gigahertz. So there's a microwave oscillator. It comes down through waveguides with holes in them, and we end up with regions where the microwave fields are presented to the atoms down here. Now, the idea is that if we get that frequency right for the atoms, then we will have most of the atoms that have been selected here will then come off down here, be detected by the detector. We can measure that electronically, and we can go back and say, right, that's the right frequency. We put in a bit of a dither in there, and we can now correct for small offsets. What we end up with is our oscillator is now locked to that atomically defined frequency, and then your counting electronics sorts out the timing after that. Now, the idea that this is based upon two bursts of an electromagnetic field is something which I'm going to come back to when we look at other aspects of what we call atom interferometry later on. I mentioned the filtering that's happening in there. That's another thing which is quite fundamental in the history of quantum mechanics. If you take a beam of atoms and send them into a magnetic field here, according to the orientations of those magnets, of those two dipole moments pointing in opposite directions or in the same direction, what you would expect is that the atoms will be displaced by different amounts. And classically, you ought to be able to have any combination of those, so you would expect to get a smear in this experiment between the two, because you can have any value. And what you actually find, going back to this experiment in 1922, is that you get two spots. You don't get a smear between them. And this is a rather nice postcard that was sent by, the experiment was done by Stern and Gerlach. This was sent by Walter Gerlach to Niels Bohr, one of the other names in quantum mechanics, as a postcard, taking the plates that have been developed and a picture of those. In this direction here, don't worry about that. That's where the magnetic field is changing. What you're interested in is the middle slice of that, where you can see that rather than being filled in, it's got the two lines there. And this was evidence of something new. It was evidence of the quantization that we have in that case. So classically, we could have any value of the combination of two magnetic dipole moments. In the quantum case, when we measure it, we find we can only get particular values. And that's where the quantum in quantum mechanics comes from. I should say, we can, in the meantime, put fractions of those states together to end up with other apparent numbers. Quantum mechanics is very careful to say that it's when we measure something that these are the answers that we can get, not that that was necessarily the case in between. So what was happening with the microwave fields there? What we can imagine here, we start off with our atom. What we're going to do is actually to put it into a state which is oscillating first of all. And we do that with the first burst of microwave field. So this atom was sitting perfectly happily with the magnetic moments, where are they, like that. And then we come along with the field and we make them wobble a bit. And then we turn that field off because they're moving between the two regions. And when we get to the second one, they encounter that field again. And the question is, are they still moving in step with that, or have they got out of step with it? If they're still moving in step, if they're still in phase, what we'll find is that we keep putting more energy into that, and they remain in that, they come out into this path down here, and they remain in the direction we want to capture. But if rather than being, if our electric field is pointing upwards at that point, if rather than being with that phase, they have the opposite phase, then in fact they will end up coming out in the rejected direction down here. So that's what we're measuring in those cases. And this idea that what we're doing is taking something and initially giving it a kick with a resonant field, and then coming on later on and checking whether they are still in phase with that field or not, is the crucial aspect to a lot of the quantum technologies that we're going to be dealing with. That's as far as I'm going to go for the time being with the timekeeping. Can I ask do you have any questions about what I've been talking about there, or any of the aspects of the quantum mechanics that I've been introducing there?
Any questions? Professor, maybe I can ask one. So you were demonstrating extraordinary frequency stability or time stability.
Yes.
How do you measure that stability? I mean, in general, we refer our clocks to something more stable. But if you are talking about 10 to the minus 18, what do I refer it to? Or
it's a very good it's a very good question. And I mean, there are a number of answers to that. The first thing is that we cheat to a certain extent. We define the second in terms of that frequency. So the question in lots of ways is, what is the stability of your clock relative to that? And one of the ways you do that is to get multiple clocks and compare them with each other. Clocks in different places around the world can be connected through fiber optics and so on. And you look to see what the relative stability is of those. So really you do it by comparing all the clocks that you've got.
Similar clocks.
They can be different clocks as long as they're good. and that's what you end up looking at.
Is it something like, if you increase the number of clocks, your noise improves by square root n?
It will do, and that sort of thing is done. But if you have two clocks and you can see how much they drift apart, then that in itself is a measurement of the stability in that way, if they're independent. Yeah.
Okay.
Yeah. Okay.
Any other questions?
Well, on that point, that is Allen variance. All about that, right?
Exactly. Yeah.
We can compare the clock by them.
Yes.
You don't necessarily need to have 10 atomic clocks. You just run a clock for a long time, and then got the Allen variance, and then you'll see the stability.
You do. You need a decent time base for the Allen variance measurement. But yes, that's what you're doing. Yeah, and the Allen variance is the usual way of presenting this as well. Yeah. Yeah.
It is simple as Allen variance. Then I apologize for my question.
If the use of the word simple is correct, then yes.
The Allen variance is commonly used in the inertial world. It
Yeah.
was very common.
Yeah. Yeah. Okay. So I'm going to spend a bit more time looking at inertial measurements, but I'm going to base it upon some of the ideas that I've presented to you from the timekeeping. First, though, I'd like to look at a navigational analog, which goes back quite a long way. I need to check the date, 1714. Now, not long before then, my notes might tell me, here we are, 1707. The glorious British naval fleet was returning from Gibraltar and sailed through storms in the Bay of Biscay and got the navigation wrong. And as a result, 4 ships went aground on rocks that were where they didn't expect them to be. And something between 1,500 and 2,000 sailors lost their lives. As today, it takes a big accident to change things. And that big accident prompted the offering by Parliament of the longitude prize to people who could come up with a good way of allowing you to determine longitude while you're at sea. What's longitude? Longitude is how far east and west you are. Latitude isn't too hard. You look how high the sun is at midday and you can work it out from that. But longitude is tricky. And there were various attempts over the years to do this, but none of them really worked well enough to stop your ships going aground. And there's a beautiful story, which you've probably seen the books and the films about, as to how this individual, John Harrison, essentially dedicated most of his life to making clocks that were good enough to be able to help you determine longitude. This was one of the early ones, and he was already trying to design clocks that would withstand the motion of a ship. So in this case, you've got some balance in the mechanism so that the rocking didn't disturb it too much. But what was the principle that he was using there? Well, the principle was to combine, first of all, a precise clock, but also some sort of astronomical measurements, typically with the sun. So what you would do at the point that you set off, you would monitor the height of the sun to determine when midday was, or with a bit of luck, there was an observatory nearby. Find is that your clock was keeping the local time where you set off, but your new measurements would tell you the time of the local midday at the point that you were. So you'd measure the midday using a sextant, something like this. And I've put these slides in just to show that sextants have been used in navigation up to really quite recently in airliners and the space shuttle, still regarded as an important navigational instrument. But what we're going to do now is to measure the time of that clock, the phase of that clock, relative to the illumination as we go on. So the Earth is rotating, the position of midday is moving around the Earth, and what we're going to do is to compare that point with the clock that we've got here. So that's the principle of measuring longitude that was developed 300 years ago. What we do now with our atoms is to scale that down. So rather than these bands of light and dark that have a wavelength of the circumference of the Earth, we take a laser beam whose wavefronts are a micron apart, and our clock is going to be an atom. And the idea is that if that clock was, maybe I'll just go back a second for that one, if that clock is stationary, then it's always going to be keeping phase with the wavefronts there. But if it moves, as it will do in a moment, so with that going around there, it's always hitting the top where the black bar is. If it starts moving, then it will hit 60 seconds at different parts of that wave, and we'll get a different phase measurement in there. So we're taking the Harrison principle of determining longitude and scaling it down to the atomic scale. And that is actually how we do a lot of measurements now The clock, the atomic clock, was working in that principle, but what we were doing was setting the atomic clock going with that first bunch of microwaves and then checking the phase later on relative to microwaves coming from the same source. But that's fundamentally what we do with inertial measurement as well. There are some differences when we're looking at inertial measurement in the technicalities. I'm going to start talking about a laser beam rather than a microwave field. We have different ways of preparing the atoms and so on. But the principles are going to be the same. So for the clock now, this is going to be one of our atoms. What we're going to have, instead of those two bursts of microwave, is bursts of a laser beam, which is traveling in this direction. And the fact that I've switched to a laser beam is useful because that now has a short wavelength. Microwaves are very long wavelength. Now we can notice the fact that the atom is going to be moving relative to those wavefronts in here. So we're going to set it going with one pulse and pick it up and measure it sometime later on. Now we will come back to that, but what I've introduced there already is this idea of waves and particles. We're now starting to treat our atoms fundamentally as wave sources, as if they were water waves moving around, electromagnetic waves moving around. And they show all those classic bits of behavior that we get from waves, that if we combine them frequency is that we have there, that's the uncertainty principle. And of course that they will move and propagate, or they may be confined in a place where we get standing wave solutions. Now in quantum mechanics, we say that these waves are mathematically written as a wave function. We usually use the Greek symbol psi for that, and that's a function of position and time, and that, according to the principles of quantum mechanics, can tell us in some recipe or other, we can extract all of the relevant properties of that particle from that. I will mention here, because this is usually a confusing thing, the mathematics of it, we usually use complex numbers, and what that allows us to do is to combine both a snapshot of the spatial variation, but also what the velocity is of that wave, how it's changing. If we just had a real number, that would only represent how much there was at that time and not what its time dependence was. And those waves have a wave equation very similar to that for electromagnetic waves or water waves or any of the other waves that you like. It's the Schrödinger equation, and that's the one that we always use, but think of it as a wave equation. We're not going to go into it any more detail today. Now, as I said, you can extract a lot of things from that. The way you do that is to essentially form some sort of calculation average or a weighted average of a property. So in each of these integrals I've put down here, we have an integral over all space, something that depends upon the probability of the particle being there and then the thing we're trying to measure. So if we've got the total energy, we calculate the energy at different positions, what the probability is of being there, add all that up, it's just statistics. And that way we end up with a total energy, a momentum, and a position. That's how we treat this Schrödinger wave function in order to generate the particle-like properties of energy, momentum, and indeed where we might think the average position of that particle is. And the fact that I've written down energy there and momentum for the particle properties, remember, we're thinking of waves. Waves usually have frequencies and wave vectors or wave numbers, and they're related in this sort of way here. So we can actually take or put in our factors of Planck's constant and write frequencies instead of energies and wave numbers or vectors instead of momentum. Now, the fact that we can write out expressions like this means that the position and momentum are Fourier conjugates in the same way that the time dependence of a signal and the spectrum of it would be related through a Fourier transform. So if you're thinking about the frequency response of a system and relating that to the time response, you're doing exactly the same thing as switching between position and momentum for a quantum particle. And that means that the bandwidth theorem that applies to electronic signals also applies to quantum systems, but we put some factors of Planck's constant in and we call it the Heisenberg uncertainty principle. So if we define the position of a particle very well, equivalent to having a very narrow wave packet or a very short signal in electronics, then what we'll find is that we have a great uncertainty in the momentum in the same way that we'll have a great spectral width to our signal in that case. If we put all that together, we end up with a relationship that says that when we're dealing with energy and momentum, we're really dealing with frequency and wave vector, but with a factor of Planck's constant thrown in. Okay. Now I'm trying to, first of all, any questions at this stage? I'm going to try to build this together and to see how we can put together our inertial sensor in a moment. No, everybody's stunned there, splendid. So I thought I'd take another, not quite an example of a navigational device, but something that you might come across in a navigational environment, which is the bosun's pipe. And you see this when the Navy is being very formal and one of the big officers comes on board and you have a pipe, then it goes beep, 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 according to where your hand is on that whistle. So how is that whistle working? What you've got within that whistle is a cavity with a hole in it, and you're blowing some turbulent air over the top. And what you will then therefore do is to excite standing waves within that chamber. And I've kind of slightly schematically here shown what the distribution might look like. So probably the easiest one to set up is a low note like this one here. But if you shape your hand over the top of it, then you can manage to force it to go into an overtone here. So in that case, we've got waves in cavities, and the result of having an edge to that cavity is to mean that we end up with standing waves, particular modes of oscillation that we have there. So within that cavity there, we might, for example, for the higher note, have something that looks like that. Now, again, what we can do is shrink that down to an atomic scale. And if we look, and again, slightly schematically here, at an electron which is confined within the potential of a nucleus. The nucleus is positive, the electron's negative, it wants to be close to the nucleus there. In the same way that the air is confined within the bell of that whistle. And what we see is that has an anti-symmetry. This is showing the incorrectly labeled, really. This is showing mod squared of this. One side should be positive and the other side should be negative. So same probability, but opposite signs. And in fact, these states correspond to those two energy levels that I showed you earlier. So this has a higher energy. And when we put these together, we will get a beating between them. We can try to do that here. So two states like this, two modes of the whistle. If I could excite both of the modes of the whistle at the same time, which technically is possible, but I suspect is hard, then what we would hear is a sort of rapid beating between those modes at the difference in frequency that they had. And in this case, the difference in frequency, which corresponds to the difference in energy on our energy diagram, we will get a beating. And if we add them together, we can see that that's giving us probably not from the back, but you should be able to see that sometimes the right-hand part of this is positive and the same phase as this, and sometimes it's the left-hand part that's positive. And the overall superposition sloshes backwards and forwards at the beat frequency that we have, which is that 9.1 thing gigahertz that we had for cesium. So it looks very much, our quantum picture looks very much like we have in a classical picture, where the electron is sort of moving its center of mass left and right around the nucleus there. Now, I'm going to show the same picture over here, but let's have a look at what's happening now with these states in this case. I'm starting off with my atom in one of these, the ground state as we call it over here, and I'm using my first pulse of radiation to put it into a superposition, equal parts of these two, which is now a classical oscillator, which is moving backwards and forwards like this. That's my clock. It's sitting there moving backwards and forwards, but the whole lot of it is drifting relative to the laser pulse, the laser wave fronts down here. And when I ask again what's happening, what I'm going to do then is either to keep driving it and end up in entirely this state, or I get to undo that operation and end up back down here. And what I read out is how much of the populations are for these two states. So we've got a different picture now. We started off by thinking of this as classical oscillators, acting as clocks with a well-defined frequency. And what we're starting to see is we're thinking about interfering waves. So if I had a beam of light that was broad and I split it into two beams, what I would expect is to get some interference between those two beams in the regions where they overlap. And that's what I'm measuring. So first one is creating the two beams, and the second one is going to measure it. Now we can use that as a way of measuring velocity. I'm not really going to tell you anything new so far. What we did at the beginning was to talk about measuring longitude as to how far you had moved around the globe. And if we know how long that took, we're measuring velocity. So we can do that in this case. And what I'm going to show here is what happens if we measure the probabilities according to how far apart our two probing pulses are. And what we'll see is that if we take one velocity of atoms, then we get one shape of curve like this. And if we take a higher velocity, then we'll get another of these curves coming down here. So different velocities will give us different responses at different time periods between these. How many oscillations have happened at that velocity? How many fringes has it crossed in that time? And we can put that together, therefore, because our total signal that we get is the sort of brownish dotted one here, which is the sum of those fringes for all of the different velocities that we've got. If we Fourier transform that total signal, what we're going to get is a distribution of velocities down here. Let me quickly go over that again. If we cross one fringe in the time that we've got down here, if we've got a slowly moving atom, we have to wait a long time to get to that, where are we? So that one fringe there. If we have a faster moving atom, that will occur at a shorter time. Filling in between those, what we're going to measure for a single velocity class is one of these curves. But for different velocities in our distribution, we're going to get different periodicities in here. The sum of all of those, as in signals when we add lots of different frequencies together, is giving us information that we're after about a velocity distribution. So we can take a measurement like that, perform a Fourier transform, and produce a velocity distribution down here. Just take my word for it. Here's some experimental data. So what we did in our experiment was to change that period between the pulses. We could cheat and switch artificially the phase of the probe pulse by 90 degrees to get a quadrature measurement. And we can Fourier transform that to find that in our atomic system, we had a distribution of velocities like this. You might notice the temperature that we have here. We're dealing with ultra-cold atoms. We use some techniques to do with use of the Doppler shift, effectively, which allow us to end up with temperatures in our atomic clouds that are in the microkelvin range. And if you work a bit harder, you can get down to the nanokelvin range. And we do that so that the atoms don't fly off and hit the sides of the apparatus very quickly. Now, a velocity measurement of atoms in your system is not helpful for measuring inertial movement, because those atoms started off at the same velocity as the apparatus. So that's not useful. What you would like to do is to measure the velocity of your apparatus, not the velocity relative to something that started off in step with it. What we're going to do is to come up with a way of making a differential measurement so that we can get acceleration. And the way that worked, the example here is to go back to 1940s, and a lot of navigational aids were being developed for military reasons, and this is one to help bomb a target, or specifically in this case, to lay down pathfinding flares so that the bombers could come in afterwards. And what you had was a guide beam that the aircraft would fly along here. I'm not going to go into how that works, though it's interesting in its own right. But you then had a series of other beams that were sent out towards but just ahead of the target here. Now, the specific problem this was to counter was the fact that although you could fly along this beam and know that you were flying overhead the target, you didn't know what your speed over the ground was because you had different air speeds and you wanted to compensate for that. And the apparatus worked by having, first of all, a sort of a beam here that told you were getting close, and then two beams here that were very specifically set up so that the distance between them was the same as the distance remaining to get to the target. And the other piece of apparatus, clocks keep coming up in this, was a specially adapted stopwatch. And what you did was you zeroed the stopwatch, first of all. When you crossed the first beam here, you started it. And when you crossed the second beam, you pressed a magic button in there that had been added that reversed the direction in which that stopwatch went. And when it had counted back down to zero, you knew that whatever the speed you were going at, then you would have gone the same distance as you had in the first one, and you could release your bombs then. And if you wanted to take account of some slight inertia that they had, you could release 5 seconds early or something like that. So this is the basis for making a differential measurement using our velocity technique. What we'll do is to make, this is one of our velocity measurement techniques, and then this is another one here. And if we make it join them together, what we have here is essentially two operations that together mean that what was in this state is taken down to this state, what was in this state is taken down to that state. This second system undoes the effect of the first one, provided that the velocity remains constant. But if it doesn't remain constant, what you get out at the end is a measurement of the difference. The difference in velocity over time is an acceleration. So when you're looking at quantum technologies that are measuring acceleration, or are measuring gravity, or are measuring rotation, because they use the Coriolis acceleration as the way of determining it, this is the principle that's used. It's two of those two pulse interferometers put back to back, but we will usually merge these middle ones into one longer pulse. And that's what's shown schematically down here. You can imagine laser intensity up this way and the time scale moving on here. Now, if you look at the trajectories that those atoms will follow in that case, imagine we're lobbing them up in the air so that they don't have to be, but we might start off by at least trying to keep them on the picture by lobbing them up in the air. What we do with this first pulse is to separate those paths. And if you like, the atoms that are following this path and have transitioned to this state here have absorbed the momentum of that photon that was moving up, so they've got a bit of extra lift. At this point here, we reverse them. So we take that momentum away, we put them into that one, and lo and behold, they recombine again back at this point here. And what we measure is the difference in time it's taken effectively between these two paths here. We can write that out in different ways, but think about the difference in time it's undergone. And that tells us about the acceleration that they've experienced. And that could be the inertial acceleration. It could be because actually the apparatus is fixed and you're measuring gravity, or it could be because the apparatus is rotating and you're measuring centripetal acceleration. I shan't say too much about this. This is really redrawn again, but when we think about optical interferometers, then the optical analog would be something where we had mirrors in these places here. And what we're doing is taking a beam of a wave and splitting it and then recombining it back up here. So we draw pictures like that. It's the exact equivalent that we've got there. So I think I'll skip through these. What does the apparatus look like? Now, I'd like you to remember those pictures of the early transistor. This is not refined stuff at the moment. This is in labs being put together out of lots of different components, not all of which we can buy, some of which we have to make. They're quite complicated. They start off in the middle with a vacuum chamber because we don't want the atoms banging into things. They're surrounded by all sorts of, well, vacuum pumps, optics, electrical connections so that we can heat up the sources, detectors, cameras, that sort of thing is what's going on inside there. You'll notice there are some magnetic field coils here as well. Those are used as part of the technique for reducing the temperature down to the microkelvin range in the first place. And we also, in general, would have to surround this in magnetic shielding as well, because the magnetic fields will affect the measurements. And then the apparatus is put together, and you're not going to look at the details. The important thing is there's lots of it. All of these are complicated pieces of apparatus. But what you get actually in this case, this is looking through one of these viewports. There's a little glowing ball of atoms in the middle. So the thing we're dealing with is probably about 1/3 of a millimeter across, about 10 million atoms at a temperature of 10 micro. Now, I showed a diagram, slightly different version of it earlier, of the trajectories of the atoms in our interferometer, starting off down here, being split into a superposition and recombined here. What are the numbers in that case? Well, the most sensitive of these instruments so far is a 10-meter, it's called a fountain because it sort of sprays upwards and comes back down again, 10-meter fountain in Stanford University. If you look at the separation of these superposed components at the top, it's 0.5 meter. But they're still parts of the same quantum thing, although classically we'd say that they seem to be following quite separate routes. They've had to build something which is not particularly portable. It's several stories high, this big gantry there. If you're going to go for record sensitivity, you don't necessarily get to wear it on your watch. What else? Yes, a bit of a detail of what's going on there. Again, the vacuum gear and detection and so on. What you do get to do sometimes is to produce detailed models of it. And I don't know whether you can see from the back. This is apparently a scale Lego model of the apparatus there. And another photograph, the sorts of things you find in there, usually lots and lots of optical components is what's involved. So our challenge, which is being met at the moment by colleagues around the world, is to try to make this more portable. And of course, there's some loss of sensitivity in doing so. The ones that have been taken out into the field so far are generally a sort of 19-inch rack about this high. And I know that they've been demonstrated on ships, submarines, I think on trains. Some have been put in the back of cars. It's probably fair to say that an important part of the apparatus is a fleet of PhD students and postdocs to keep it going. But that scaling down is starting to happen even with real systems. So there's our device again, just to show you the origins of what we measure as a phase difference at the end. Remember, what's the difference between the clock and what the system is actually doing? And that depends upon a component of linear acceleration, the centripetal term in there, and there's a Coriolis term as well. So sometimes we have difficulty separating those out. I have to be quite careful about the way that we do this. Right, let's move on from that one. I showed you in that you can measure terms to do with the rotation that we've got over here. And what we're really doing there is using the atom wave as an analog of what you already have in rotation measurements. If you have a ring laser gyro, like on an airliner here, or if you have a fiber ring gyro working in essentially a very similar way. And one of the ways you can think about this is that you might imagine the two different routes on which a wave can go around here. If this is rotating, then by the time a beam in this direction has got to here, that mirror will have moved. And one of the confusions and delights, I think, of anything to do with quantum mechanics is that you can end up with what intuitively look quite different and sometimes incompatible pictures actually describe the same physics. What you can find in this case is there's something called, this is the Sagnac effect. And if you were to take this path here and calculate the area that there is between these two paths, then the phase that you're getting out here depends upon the rotation rate and that area in there, and a couple of things, the frequency and the speed of light. So there are often quite conflicting, as I say, intuitively conflicting explanations of what's going on. And one of the charms of the area is to try to work out how these actually are telling you the same thing. What we get in this case, because the Coriolis term depends upon, I think I've missed out a theta in there somewhere, depends upon the velocity that we've got up there, then what we will do is start off with a bundle of atoms in the middle. As they expand, and we take a photograph later on, where they've got to depends upon their velocity, and then the fringe phase depends upon their position then in that case, because that's related to the velocity. So we get some fringes, we measure the periodicity and the orientation of that, and that will tell us two of the rotation components that we have. And then in fact, the offset of it will tell us one of the acceleration components in that case. And down in Southampton, where we're a little bit behind some of the other experiments in this case, here is our 19-inch rack of various optical and electronics apparatus. Inside, it looks rather more like a traditional lab, but boxed up so that we can move it around a bit. Here is our vacuum chamber, just about make it inside there, surrounded by, again, optical components with fiber optic connections, cameras, and detectors and so on. That's in a precision rotation stage so that we can test it. Now that was going through quite some length and probably a number of different slightly conflicting pictures on inertial measurement, which I guess is the subject of the conference here. So what questions can I, yes, over there. Yep.
So you spoke about detecting those phase differences, and so my question is, how crucial are the distances between those two spots where you measure, as well as the distance of the waves traveling to those measuring points? So if there is any misalignment, how does this affect the accuracy of the clock?
Well, what we try to do is to make an arrangement so that we're measuring in the same place as we started off from, either because the atoms are being thrown up and are coming back down again, or on a shorter time scale because they're spreading out from the same point. So in that case, we try to make it so that there's no difference in position. What you do have is questions about the optical path that you've had before you get there and the stability of that. And we definitely see, for example, effects in the fibers that we use to deliver our lasers where there is noise that is essentially changing that path a bit. So we have to stabilize that. So yes, you're absolutely right. There are a number of points in the apparatus where stability is important. Yeah. Yep. Definitely. And this is an area where the first time that you put something together, it will be terrible. And what you then go through is a program of a lot of refinement, trying to find out where the instabilities are, making sure that everything is isolated and stabilized actively, reducing noise. Does anybody like trying to find noise sources? No. Interference, getting rid of that. And that's why, if you look at programs in particular on the clock side, which is the longest running one, those precisions come after a certain time by having real experts working on this for year after year after year to make it so that it gets very good. And some of the distances you talk about with the clocks, they tend to use an optical resonator as a sort of intermediate time base. And they have had to go into great detail in the mechanical design of those resonators to make sure that the vibrational modes of them, you know, the tiny, tiny motions that you will get, they've had to design out of or minimize as well. So yeah, there's a lot of really detailed graft behind it. Absolutely right. Yeah. Yeah.
Thank you. Can you please elaborate a little bit on how the atom interference provide advantage or quantum advantage over the classical techniques, other than the beam of the atoms being very cold?
Right. I'm pausing because I think there is a very frequently stated reason, and I'm not convinced that that's quite the important one. So the version which is stated is that you can have a very short wavelength for the atomic wave function, and that means that you have a greater sensitivity if you're measuring fractions of a cycle. But actually, in most cases, that's not the thing that's important. You're actually measuring a difference between those wavelengths, and that tends to be on a classical scale. So I think the real advantages come back to things that are perhaps a little bit more mundane. The first thing is that the atoms are all the same, so you don't have to worry about calibrating the frequencies of them. You could imagine having microscopic clocks that perform the same role, but you would have to calibrate them. The second thing is that you can find clocks which have a very, very high quality factor. In fact, a lot of the explanations that we give about how you drive a transition between different states of an atom is based upon the assumption that that is permitted by the symmetries that are involved. And what you end up using with clocks is states where they're nearly forbidden. So that you've got a very, very weak coupling, which means that they decay very slowly, so they have a very long lifetime, lots and lots of cycles essentially over which you can measure. So you've got identical atoms with a very, very high Q resonance. And one of the features of that being high Q is that the atoms are extremely well isolated.
Cold. So
well, first of all, they're cold, they're in vacuum. So it's there aren't very many others nearby. So there's not much they can do to interrupt them. Collisions with other atoms are very rare. It takes a long time for them to hit the wall. If you could imagine having nanoparticles that might do something similar, and then you've got questions about buildup of electrostatic charge. If you have an electron on, then that will then interact through mirror charges with anything that's conducting. So the fact that the atoms are identically neutral is another feature in there. You'll get the impression all the things I'm telling you are almost a classical picture of an atom. They're not really to do with the quantum wave function. They're features of them being identical, exactly zero net charge, high Q, and not banging into anything.
Yeah, I mean, that's a very honest answer. Thank you. Well, to this forum, I guess it's more relevant to, for example, compare with MEMS or laser gyros. So this is hypothetical, but if I had a gyroscope with a Q factor of 100 million, of course, that's not possible. But if I have that, then would have been similar.
Yeah.
So that's entirely classic. So maybe I'm just being a little bit pedantic on the term quantum sensing. So I think a quantum sensor and quantum sensing are two different things.
Okay. Yeah.
Probably that would be
a fair
thing to say.
There are a number of different aspects to it, and certainly there are fundamentally quantum things you can get into at the detection stage that will give you generally quite small advantages when you're getting into squeezing and use of entanglement. But
where you can break the SQL, in fact, go beyond class.
That's right. Yeah. But you have to argue in a lot of those cases, again, being honest about it, a lot of those depend upon having a very small number of particles. And in most cases, you were probably better off by having a large number of particles and getting the root n factor coming through. So I think that my feeling is that we still haven't quite worked out certainly what the right system is, but also what the right real advantages are of this, or even what the right scale is. We sometimes say, well, actually, we do better with a cloud of atoms by root n than we do with an individual atom. Would we do better if we had a nanoparticle, which is a collection of atoms with another few factors of 10 in there? What is the optimum that we get there? If we make it too big, then we end up with having to calibrate everything. If we make it too small, we don't get much signal. Where is the optimum in there? And probably the answer so far is that actually it's partly driven by what we can do, what the technological constraints are. And it's going to be really interesting to see where that develops when we start exploring more of these avenues.
Thank you so much.
Okay.
Any other questions?
Okay, so I thought to finish off, I'd look at another example, which I think, well, I think it's interesting because we're working on it, but how we can get accurate control in a real environment. And this is actually another feature of what we have to, you're talking about there. Not only do we have to get the phase stability, but actually we have to be able to cope with the fact that even at these microscopic temperatures, our atoms are moving, and they will not inevitably, if we have a laser beam or a microwave beam, the intensity will not be completely uniform, and there will be other sources of noise in the system. So when we talk about these pulse operations, then there are difficulties in implementing those. And as one example, I think I showed a couple of slides ago that the sensitivity can be written as some constants multiplied by the area that's enclosed by the interferometer paths. And usually that's quite a flat parallelogram, I suppose, in the absence of gravity, with a very small width to it and therefore a very small area. And what a lot of people are looking at is something called large momentum transfer, where rather than following this rather confined path here, what we can do is to put in extra impulses that have opposite effects on the two paths and broaden that area. In this case, just shown by n equals 2, but people have shown actually up into the hundreds implementing this to try to make that sensitivity much greater. And the problem that you have is that when we talk about splitting this into two equal components or inverting it so that what was going down that path goes along that path, we need to make sure that our laser beams are tuned to the atoms and that we turn the laser beam on and off at the right times. And if we have a variation in intensity or a Doppler shift from the atoms moving, then the right time is a different time, and therefore we don't get the same effect upon all of the atoms in the cloud that we have. This can also be affected not only by intensity variations and Doppler shifts, but if there are stray magnetic or electric fields in there as well. And what you can do, of course, is to start off saying, well, I've got 10 million atoms with a certain velocity distribution. I'll throw away 9 million of them, keep the remaining 1 million, which I've filtered out to have a narrower range. But you're now throwing away signal, which is not good. So what we have to have is a way that these pulses that are acting like the mirrors and beam splitters of our interferometer can be made to operate with high fidelity and not have too many imperfections in them. Because when we put a lot of these together, then the imperfections will accrue. And if we put 100 of them together, we have to have really, really good pulses to get anything out at the end of it. Now, happily, this is an approach or problem which has been addressed very successfully in NMR. You may remember I said right at the beginning that nuclear magnetic resonance imaging is sort of an old version of a quantum 2.0 technology. But the way they do it goes back to another navigational problem. And since we're only about half an hour's travel away from the Museum for Airships, Friedrichshafen, it's kind of nice to show a picture of an airship in here. And the problem that was solved for airships by Ernst Zermelo back in the 1930s. Airships moved relatively slowly, and in 1929, the Graf Zeppelin made a circumnavigation of the Earth, starting off, I think, in Lakehurst, traveling around through Friedrichshafen, stopped off there, over to Tokyo and back round via Los Angeles. And how do you work out what is the right route to follow if you're given some detail about what the prevailing winds are and that sort of thing? Well, Zermelo tackled this and essentially invented what's known as the calculus of variations. And the principle there is that you start off with a possible route and you consider what the effect is of a series of tweaks that are made to it. And if the tweak makes it better, then you stick with it and you keep tweaking it. At the end, the end is the important point. At the end, any tweak will make it worse. Now, the important point about that, if any tweak makes it worse, then you are essentially at the turning point when you're optimizing something. And therefore, any tweak makes it worse, but not by much because you're right at the bottom. So you've got a high degree of tolerance of small variations at that solution. Now, where are we coming now? Ah, yes, there we go. So the idea is that if you can just about see, if we put in other routes around that route, then they will essentially take the same time to go over that distance. Let's change that from saying they take the minimum time to get there to saying after that time, they will be, if we consider different paths here, they will have very little variation in how far they've gone. So we're reaching the same destination point, even if we have small variations in the path that's followed. Now, one of the ways that we represent our atomic states, actually, with a picture that looks like the Earth, we have our two states. We say, if we're exactly on state 2, we're at the bottom. If we're exactly on state 1 at the top. If we have a superposition, we're somewhere in between, and the relative phase we give is the longitude. So I can draw pictures that look like the globe that are actually representing the quantum system. And our problem is, for example, can we get from this pole here to this pole here in a way which isn't affected too much by the fact that we might have different atoms following with different speeds, or indeed with different detunings. The operations we might want to do in that case, our initial formation of a superposition corresponds to a rotation onto the equator. Our mirror pulse is a full rotation from one pole to the other. And if we were just to leave the laser off, then what we get is a dephasing, which corresponds to rotation around the polar axis there. And the catch is that if we have our laser detuned by a Doppler shift, then the axis of rotation doesn't actually lie in the equatorial plane there. It's off a bit, so we never get down to that point down there. So that is what we have if we just turn a laser on and off. We don't do anything else. We will get some fraction of the paths that are shown there. What can we do in order to make sure that all our atoms get from one pole down to the other one? Well, the first thing we can do is what was known as a composite pulse. And actually that's based upon the same thing that we had as with the X-Verfahrung here, this bombing aid. What we do is we start off by allowing the atoms to follow a quarter of a rotation, and then we take the fast ones to the back and the slow ones to the front with another rotation in there. And then what happens in the second half is that the fast ones catch up with the slow ones, and they all get to the bottom at the same time. And this was the first composite pulse that was invented in 1979 by Malcolm Levitt, who's now a professor of chemistry in our university in Southampton. So that is a way of coping with variations in intensity which correspond to how quickly the thing moves. What do we do about detunings? Remember, the detunings over here mean that we're going around different axes. And a series of more complicated composite pulses were invented. And this is one that does, so our problem is this: if we don't do anything apart from just have the detuning there, we'll end up with different final points on this sphere. So one of the solutions in this case was something called compensation for off resonance with a pulse sequence. The guys that developed these spent a lot of time working on the algorithms by scratching their heads and doing mathematics. And as far as I can tell, an equal amount of time trying to come up with fancy acronyms for the processes that they come up with. And this has a rotation around one way, back round that way, and back round this way a load further. You'll notice that these sequences are taking longer than the basic operation did, but by the time it comes around to the bottom there, then what you'll see is that actually, although they've spread apart a lot in the meantime, by the time they come down to the bottom, then they're all essentially in the same place. So people, by scratching their heads, were able to come up with these composite pulse sequences and publishing a nice range of those. What we do nowadays is we throw the computer at it. We say, you don't have to just have a finite number of these things, slice it up into 100 or 1,000 different possibilities, use that calculus of variations that Zermelo came up with in order to optimize this. And this is showing here that actually, irrespective of the starting point, we can come up with a sequence which will get us to the mirror point with a very strong coincidence there with a very wide range of parameters involved. What does that do to our overall performance? Well, I should explain. In this case, the phase pattern that we're playing is this. We're modulating the laser beam with this phase all the way through, corresponding to different rotation axes. If we didn't do that, then as we varied the detuning for an ensemble of atoms, and we've, in this case, not only got a variation of detuning, but we've allowed for a variation in intensity as well. What we find is that even at the center, then we're only getting about 75% transfer, and it's quite sensitive to detuning. The orange here is one of these sort of hand-developed composite pulse sequences called Waltz. That's doing a lot better. The computational optimization hits pretty close to 100% at the center and is much more tolerant of the detuning that we've got down there. And what people are finding is this is now giving them the performance that they need in order to really do this in practice with large number of these sequences. And on the right here, this is just another way of presenting the much broader and flatter region of optimum against the two parameters that are varying there. So I guess that's got through what I wanted to cover in terms of the navigational analogues of some of the quantum technologies, in particular around timing and inertial sensing. First of all, any more questions on that section? Okay, well, maybe I'm going to be sticking around at the end until I'm kicked out of here. So once I've had another coffee or something, I'll be very happy to answer individual questions then. I do like this way of trying to draw upon classical analogues of explaining things, and we've used a number of these things here. There's an awful lot of intuitive interest in these old techniques and a lot of ingenuity that went into them. So I hope, thank you very much for bearing with me and indulging me in my interest in these. There are quite a lot of analogues we could follow up. This was a list we put together where there's a wide range of quantum technology phenomena and classical navigation illustrations of the techniques. I've only really drawn upon a few of them today. I'm sure there are more out there to find as well. But do drop us a line if there's anything. We're actively involved in developing both the rotation sensor and the optimal control solutions in our experiments. Do get in contact if that's of interest. I will also, if you'll permit me to, just acknowledge some of the people who've worked with me in my group on this or done most of the work in our group on this over the years, and some of the collaborators that we've had the pleasure of working with. Thank you very much for coming along today and giving me an audience.